Okay. Yeah, it's my great honor to be here today to share with you our recent work on the non-flammable electrolyte for large-scale rechargeable battery. So as you probably know, the energy crisis and the global warming are two greatest challenge. Many government has pledged to achieve net zero carbon emission by 2050. And the International Energy Agency has set out a pathway to achieve this goal. You can see from this figure, by 2035, no new internal combustion engine car sales will be permitted. By 2050, almost 70% of electricity will be generated from solar PV and wind. But we all know clean energy such as wind and solar energy are intermittent. To use this clean energy for various applications, we need to properly store them in energy storage device, that is batteries. So battery has been used for various applications. For different applications, the requirement of the battery probably slightly different. For portable device, electric cars, high energy density, we hope the battery can store more energy, right? And we hope the battery can be fast charged. And of course, it got to be safe. But for the large scale, especially great scale energy storage, because we have a large space to accommodate those battery pack, so the energy density become less critical. Instead, the cost of the battery and the cycle life of the battery is more crucial. And of course, safety is no matter for what kind of application, safety is always the key parameter we need to pay attention to. Then you probably know the electrolyte actually is the reason for the instability of the lithium-ion battery, because the lithium battery uses organic flammable electrolyte. And not only the safety electrolyte, not only influence the safety, but also it influences the electrochemical performance of the battery, because the battery reaction is just the electrode interface reaction. So the stable electrochemical working voltage window depends on the Lumo-Homo value of the electrolyte, of the anode and cathode, and also the stability of the electrolyte. And we often call it solid electrolyte interface. It's often generated due to the reaction between the electrode and the electrolyte. This is crucial for maintaining long cycle life of battery. So currently, electrolyte is very important for safety, for electrochemical performance of all different kinds of batteries. So today, I would like to share with you our recent work on the electrolyte, especially for the non-flammable electrolyte to achieve a high safety rechargeable battery. The first example I would like to share with you is a liquid non-flammable electrolyte we developed for lithium metal battery. So this electrolyte, you probably know lithium metal, to achieve this non-flammability, we often need to add in fire retardant. But lithium metal is not stable in the fire retardant. So to make it stable, we added another second lithium salt. This is lithium nitride. This lithium nitride has a similar donor number to the fire retardant. In this case, we use TMP. So these two components have similar donor number. Therefore, the ion nitrate can readily be involved in the salvation structure of the lithium ion. Therefore, it can reduce the polarity of the electrolyte, make it more stable. And also from the calculation, we found that the Lumo value of the electrolyte increase. So indicating the electrolyte more stable. And from the MD calculation, we found for all 6 possible solvation clusters, the ESP value all decreased, suggesting that lithium metal is stable in this electrolyte. So then we found that this electrolyte cannot be ignited, it's non-flammable, and the viscosity of the electrolyte is quite low. The ionic conductivity of the electrolyte compared to most of the published liquid electrolyte is high, actually. So make it very promising to be used in the lithium metal battery. Then we evaluate the electrochemical performance. We found in the lithium copper asymmetric cell, the average cooling efficiency is about 99.5%, suggesting the lithium plating strapping reversibility in this electrolyte is quite good. And also, we found that the lithium deposition in this electrolyte is quite large piece and quite dense. On the other hand, for the baseline electrolyte, without this, for the baseline electrolyte, you can see the deposition is quite porous and not as dense as the deposition in our non-flammable electrolyte, suggesting the plating strapping reversibility not as good as our one. And then we tested the full cell in this electrolyte, use lithium iron phosphate as cathode, metal as anode. The mass loading for the lithium iron phosphate is quite high, 14.3 milligram per centimeter square on the lean electrolyte. The cell can be dischargeable for 150 cycles with capacity retention about 80%. And to maximum the energy density, we also use NCM811 as a cathode with mass loading 16.7 milligram per centimeter square. And also, again, under the lean electrolyte condition, the cell can be discharged for 100 cycles with capacity retention about 80%. So this cell, although the performance is not perfect, but remember, we not optimize the cell configuration. And this is just demonstration. This electrolyte is good, it's compatible with lithium iron phosphate, NCM811, and lithium metal. So it has potential for the real application. So these slides, we compared the cooling efficiency, the cost, and the flammability of our electrolyte compared with a lot of reported liquid electrolyte reported so far. You can see the green color means non-flammable, the red one means flammable. And you can see our electrolyte has it exhibits one of the best cooling efficiency and with a low cost because lithium nitride is relatively cheap. So this is a non-flammable electrolyte we developed for lithium-ion battery. You probably know my group also working on other secondary battery, including sodium, potassium, and zinc ion for target on large scale, especially great scale energy storage, because this battery system, their electrode material is more, the element more abundant on Earth's crust. Therefore, it could be cheaper, potentially could be cheaper compared to lithium-ion battery. But potassium and sodium are quite, reactive. So to achieve real application, we need to maintain the safety of the battery. So non-flammable electrolyte also very essential. In this case, for the potassium-ion battery, we employed fire retardant TEP as single solvent. Use this solvent to dissolve TFSI potassium salt, and we can develop a non-flammable electrolyte. We can see the electrolyte can't be ignited. When we remove the light away from this filter paper with the electrolyte, it can't be ignited anyway. So suggesting it's not flammable. And also we found that this electrolyte ionic conductivity quite good, quite high. The viscosity is relatively low. From the Raman analysis, we found nearly 70% of the TEP, the solvent, associated with potassium. So that means the free solvent amount is quite low. Then we tested the potassium copper asymmetric cell using this in this electrolyte. we found the cooling efficiency quite high, average cooling efficiency 99.60%, suggesting the potassium plating strapping reversibility quite good in this electrolyte. We also test a commercial graphite anode in this electrolyte. We found it can be discharged more than 300 cycles and without obvious capacity decay. And the average cooling efficiency, about 99.7%, is better than the other carbonate-based electrolyte. Then to understand why this electrolyte performs so good in the cell, we did TEM and FTIR mapping. We can see after charge discharge, this SEI layer formed on the electrode. The thickness of SEI around 10 nanometer. And from FTIR mapping, we can see the surface layer is very uniform, indicating the SEI is quite uniform. And after 200 cycles, the thickness of SEI layer around 13 nanometer, not big change compared to the original state. And we found that the concentration of the salt play very important role. If the concentration very low, let's say 0.9 m TFSI in TEP, we can observe a peak corresponding to phosphorus, indicating there's decomposition of TEP on the surface of the platinum anode. So if we increase the concentration to 2 m, this peak disappear, suggesting TEP not decompose anymore. So the SEI come from the decomposition of the TFSI, that's salt decomposition. So that sort of decomposition often from fluoride-rich SEI, it's often dense and has very good mechanical property. So basically, by using the fire retardant and single solvent, we can achieve non-flammable electrolyte and with very quite good electrochemical performance. So how can we further improve the performance? So apparently from the previous work, we found only 70% of the solvent associated with potassium. If we can achieve 100% solvation, then we can just prevent the 100% prevent the decomposition of the solvent and further tune the chemical composition and morphology of SEI. So keep this in mind, we found TMP, which has a higher dielectric consistent, and so very likely getting to the solvation shells of the structure. And also this TMP has a lower viscosity, has higher ionic conductivity. So it seems quite ideal to be used as solvent for the development of non-flammable electrolyte. So then we dissolve TFSI in the TMP to form the electrolyte. The ratio 3:8 equivalent to the 2M, similar to the previous work. And we found by using TMP, we can achieve 100% solvation. And the cell, by using this TMP-based electrolyte, can be discharged for 2,000 cycles, more than 2 years, with capacity retention still about 74%. And from the in situ optical microscope, we found this electrolyte can achieve dendrite-free zinc deposition. You can see after continuing 30 minutes zinc plating strapping, we cannot observe any zinc dendrite formation. While in the carbonate-based electrolyte, we can clearly see some gas bubbles appear, large dendrites, and also dead potassium accumulate on the surface. So from the Raman analysis, we found when we increase concentration about 3 to 8, that means about 2 m, nearly 100% of the TMP associated with potassium ion, that means it's getting to the solvation structure. So there's no free TMP molecule. Therefore, the TMP won't decompose on the surface. So firm, the fluoride-rich SEI, this SEI quite dense and uniform, therefore can achieve very good potassium plating strapping reversibility with cooling efficiency about 99.6%. But at diluted at low concentration solvent, although the solvent is still fire retardant DMP, but because there's some free molecule there, it may form phosphorus-based rich SEI. This is SEI not as dense as fluoride-rich one. So therefore, we can see here, if we pre-cycle the electrode in the diluted in the low concentration electrolyte first to in the high concentration electrolyte to form the fluoride-rich SEI, but later on, if we cycle in the low concentration electrolyte, still the capacity drop very significantly. So basically, the concentration is quite important to maintain the long cyclability in this case. So this is our work for the development of non-flammable electrolyte for potassium-ion battery. Next, I will move on to the aqua-based zinc-ion battery. We particularly interested in the aqua-based battery because the water-based solution is intrinsically non-flammable. It's safe, intrinsically safe. And also zinc has potential minus 0.76 versus SHE. So it can be directly used as anode in the aqua-based zinc-ion battery. Zinc is quite abundant on Earth's crust, so, and also environment friendly. All of this makes the zinc-ion battery quite promising alternative battery system for the great scale energy storage. However, the lifespan of zinc-ion battery so far still not satisfactory. The reason for the poor cycle life related to all three components. For the anode, during charge discharge, the zinc dendrite could grow, and this corrosion reaction between of the zinc, which evaluate release hydrogen. For the cathode, you know, the majority of the cathode still dissolve in the electrolyte and suffer from structure collapse during charge discharge. So far, still no ideal cathode material could be used for the zinc-ion battery. And also the water-based electrolytes, electrochemical window quite narrow, which makes the energy density of this battery system quite low. And the high water reactivity will lead to a lot of side reaction between the electrode and the electrolyte. So all of this we have to address before we can achieve a zinc-ion battery with a very satisfied lifespan. So now, from 2020, my group, probably 2019, my group started to work on zinc-ion battery, aqua-based zinc-ion battery. This is our first work. In this work, we try to compare, to understand how the salt, you know, zinc salt will influence the electrochemical performance of the battery. So in this case, we compared sulfate, and acetate. We found that this different zinc salt not only influence the pH value of the electrolyte, it also actually significantly influence the zinc deposition behavior, also the cathode electrode behavior. In this case, we found the zinc deposition is more, reversibility is much better compared to in the acetate-based electrolyte compared to in the other two electrolytes. You can see here the SEM image. This is a pristine zinc surface, quite smooth. This is a sulfonated, zinc cycled in the sulfonated and the sulfate-based electrolyte, you can clearly see the porous and dendrite formation on the surface. In the acetate-based electrolyte, after cycling, you can see the surface is still quite smooth, and the efficiency, cooling efficiency in the acetate-based electrolyte is much better, indicating the plating strapping reversibility is good. And we found that this electrolyte not only influences the zinc deposition behavior, but also influences the cathode material rechargeable, the reaction. You can see in the sulfate, traditional zinc sulfate electrolyte, manganese oxide has a 1 electron transfer reaction from manganese 4+ to manganese 3+. So it's solid reaction. Therefore, it suffers from like manganese dissolution and also the the phase transition. However, if by using this acetate, actually we can unlock the manganese 4+ to 2+ reaction, make it deposition dissolution reaction. So it means from solid to liquid solid. So in this case, we don't need to worry about the manganese dissolution and the phase change and the structure degrading as well. So you can see this is a in situ at TEM data. When we charge to a certain capacity, this manganese oxide deposit on the surface of the substrate on the cathode side. When we discharge it to certain voltage, this manganese oxide start to dissolve. When we deep discharge 1.0 volt, almost all manganese oxide dissolved. So verifying the reaction is actually deposition dissolution reaction. From the discharge curve, we can also see the difference. In the sulfate and the sulfonate, we can see there's 2 platinum corresponding to the zinc and the protein intercalation, right? But for the in the acetate-based electrolyte, we can only observe 1 platinum. So, and the voltage is higher compared to the other 2 electrolytes, indicating the reaction mechanism is different. And from DFT calculation, we found, the acetate group can strongly absorb on the surface of manganese side of manganese. So in this case, it can reduce the barrier for manganese dissolution, unlock this manganese 4+ to manganese 2+ reaction. So makes the dissolution deposition reaction possible. So in this case, so the active material manganese was dissolved in the electrolytes, existing in the electrolyte in the very beginning. Then we discharges it deposit on the surface, then dissolve. So it become reversible, and the reversibility quite good. However, you may notice the area capacity here is quite low, 1 milliampere-hour per centimeter square, because the manganese dissolution only we can dissolve limited amount of the manganese in the electrolyte. It's easily saturated. So if we want to further improve the area capacity of the cell, we need to probably either modify the cathode substrate or pre-deposit some manganese oxide on the surface on the substrate. So besides this electrolyte salt, we also look at some interface. It's traditional, to address the strapping plating dendrite growth issue. Normally, from the experience of lithium-ion battery investigation, we know we can create some stable uniform SEI layer on the surface. In this way, can superize the dendrite growth and the set reaction between the electrolyte and the electrode. So, however, in the liquid, in the aqua-based electrolyte, it's hard to form dense and uniform SEI layer because the reaction products always porous. couldn't protect the zinc anode in the following cycling, or it could release a lot of gas, hydrogen gas. So to in situ grow a stable, passive, effective SEI on the surface of zinc anode, we need to add some additives. So in this case, we adding zinc dihydrophosphate as an electrolyte additive. It could react with the OH group in the which released from the corrosion reactor in the very beginning, then form this zinc phosphate. This zinc phosphate will deposit on the zinc anode, acting as the in situ SEI layer. So this zinc phosphate is a fast zinc conducting compound, which help to facilitate zinc diffusion. From the XRD, we can clearly see this peak corresponding to this, SEI, indicating it successfully formed on the surface. And from the, after 20 cycles, zinc anode, the cross-section view, we can see the zinc deposition is dense and smooth, while in the, bare zinc anode, it's, you can see the mossy shape of the zinc deposition. And from in situ optical microscope, we can clearly see without this SEI layer, zinc dendrite grows in 5 minutes. But with this SEI layer, even after 45 minutes, deposition, plating strapping, the surface still quite smooth. From the cross-section SEM, we can clearly see the difference. So uniform zinc deposition can be achieved with this SEI-coated zinc anode. So due to the reversibility of plating strapping, the efficiency significantly improved. For the zinc copper asymmetric cell, it can achieve 99.4%. And the amazing thing is we found that this zinc phosphate not only formed on the surface of anode, but also on the cathode. In this case, we use vanadium pentoxide as cathode. We can clearly see peaks corresponding to the zinc phosphate. So this layer helped to superize vanadium pentoxide dissolution. So therefore, it played positive role on both anode and cathode material. So when we use this assemble into the full cell, we under low NP ratio and lean electrolyte condition, we can see the cell can be discharged for 500 cycles with capacity still about 100 milliampere-hour per gram. So basically, apparently in situ SEI play a positive role in improving the cell reversibility and cycle life. However, this inorganic SEI is hard to form film-like structure, fully cover the surface. And this inorganic SEI in the following cycles, because zinc plating strapping has a huge volume change, induce mechanical strain. That mechanical strain could damage this this inorganic SEI. To address this issue, we also try to create in situ organic SEI with better integrity on the surface of the zinc anode. So inspired by the adhesive property of dopamine, in this case, we employ dopamine as the electrolyte solvent additive. So during battery charge discharge, this dopamine will in situ polymerize on the surface of zinc surface. So this surface layer has strong adhesion and which guide uniform zinc flux and achieve dendrite-free surface. From the SEM and AFM image, we can clearly see with this SEI, the zinc deposition is much more uniform and surface is much more smooth compared to the bare zinc anode. So we try to understand, see the thickness of the in situ SEI layer, but because the surface is quite soft, we applied a platinum carbon protective layer and use focus ion beam to cut the surface. And from the cross-section view, we can see the thickness of this in situ SEI around 40 nanometer. It's thinner compared to the inorganic SEI. Inorganic one normally about 150 nanometer, even sometimes achieve a few micrometer thickness. So this is very important because thinner SEI can save space and without sacrifice the volumetric energy density of the battery. So this is another advantage of this in situ polymer SEI. And we found this PDA, this SEI, organic SEI, also formed on the surface of cathode. When we assemble into the full cell using vanadium pentoxide as cathode, and this SEI, because it covers the surface of vanadium pentoxide, can superize the cathode dissolution. We can see from the separator, without this PDA layer, after cycling, we can clearly see the color changed due to the dissolution of vanadium pentoxide. But with this organic SEI, the surface is quite clean. So demonstrating, the separation of the dissolution of the vanadium pentoxide. Then the full cell, we can see with a low NP ratio, lean electrolyte can be charge-discharged for 1,000 cycles with capacity retention about 150 milliampere hour per gram. So apparently, this organic SEI help to achieve dendrite-free zinc anode, significantly improve the reversibility of anode, and also superize cathode dissolution, help to maintain the reversibility of cathode as well. Combine this together, it can achieve very good full cell performance. So then, if you work on the lithium or sodium-ion battery, you probably know the researchers in the field actually tried a different kind of artificial SEI, including organic, inorganic, or inorganic composite. In the aqua-based electrolyte, we also try to understand which kind of SEI is the best. In the past, we compared, we create organic and inorganic SEI and compare their performance. Now, can we further improve the performance by creating composite SEI? So keep this in mind. We employed TEP, which is a kind of a fire retardant. We selected TEP because not only because it's a fire retardant, but also it has higher donor number compared to water. So it's readily involved in the solvation structure of zinc. So also the TEP could form strong hydrogen bonding with water. In this way, it can reduce water reactivity. So superize the cathode dissolution. That's why we call it 3 birds by one stone. So by using this solvent, TEP adding solvent, we can actually can solve the issue of cathode, electrolyte, and zinc anode. So from detailed IRM spectrum and also the functional group mapping, we found the TEP in the electrolyte, in the battery charge discharge could form a composite SEI layer on the surface. It's polymeric phosphate zinc plus zinc fluoride. That's why we call it organic, inorganic SEI, because this metal phosphate is polymer-like structure. This SEI, because the TEP also has strong hydrogen bonding with water, reduce water reactivity. So you can see the separator is quite clean, means the vanadium pentoxide in this case not dissolve as well. So the full cell in this electrolyte, in this hybrid electrolyte, under lean electrolyte condition, low NP ratio 2, it can be charge discharge for 1,000 cycles with capacity retention, nearly 200 milliampere hour per gram. It's even better than the previous, in situ organic SEI data. So apparently, we compared 3 different kinds of SEI and their influence on the electrochemical performance of zinc-ion battery. Besides that, we found, the composite SEI, if there's organic and inorganic component, the distribution of each component may not that uniform if you look at a nanometer scale. So if we can develop an SEI with monolithic phosphate structure, then could be even better. So this is my postdoc fellow, Dr. Sailin Liu. She look around all other, co-solvent that could be used, especially fire retardant, because we want to keep the non-flammability of the electrolyte. So she found actually this DMMP is kind of retardant, fire retardant, has a higher dipole moment. So this higher dipole moment could make this electrolyte readily generate interface reaction and form different kind of SEI. So then she used DMMP as a solvent, dissolve the zinc salt and form electrolyte, then tested the zinc copper asymmetric cell using this electrolyte can achieve average cooling efficiency 99.91%. This is very good. And the cell in the zinc asymmetric cell in the DMMP electrolyte can run for more than half a year and still keep very good reversibility. But however, she found the pure DMMP electrolyte seems not friendly with cathode because the ionic conductivity not good. So in order to boost the cathode performance, she added 10% water and formed hybrid electrolyte. And found this hybrid electrolyte still work well. Its corrosion rate reduced and the electrochemical stability window quite wide, 3.3 volts, better than the other electrolyte, than the water-based electrolyte. And the zinc copper the symmetric cell cooling efficiency is still 99.5%. And then she assembled the vanadium pentoxide zinc full cell and found that this full cell can be charge discharged for 4,000 cycles with capacity retention 82.2%. And she also assembled a punch cell with a high mass loading for the cathode material, nearly 16 milligram per centimeter square. After 100 cycles, the capacity retention still 81%. So since this hybrid DMMP water hybrid electrolyte has very good behavior performance when used as electrolyte for zinc-ion battery. So then to understand why DMMP water hybrid electrolyte performs so good, we did a theoretical computation and found the solvation. The DMMP strongly interact with the zinc ion, stronger than the other solvent and iodine. And also from the in situ FTIR of DMMP as an interface is quite high. And once it charged, the concentration reduced, and therefore suggesting the DMMP, is the main component that decompose at the interface. Then she did a detailed calculation, try to understand the SEI, and found the SEI around 300 to 350 nanometer, and from cryo-STEM, the component of the SEI basically consists of like amorphous zinc phosphate, some zinc phosphate, and meta zinc phosphate. from the XPS, she found although with the aging time increase, the zinc peak increase and the phosphate peak decrease, but the ratio between different components, zinc phosphate component still same, indicating the uniformity and the monophonic feature of the SEI. So due to this very uniform and monophonic feature of the SEI, this the battery using the DMNP water hybrid electrolyte exhibit very good performance. So besides this SEI, tuning SEI, trying to optimize the chemical composition and the morphology of SEI, we also use anti-solvent and co-solvent to tune the solvation structure in order to achieve better zinc electrode reversibility. So in this case, we use methanol as an anti-solvent because methanol has a smallest molecule diameter and relatively high dielectric consistent. Therefore, it can readily get into the solvation sheds. And we found this, when we increase the methanol ratio to about 50%, we can see the crystal at the bottom of this bottle. So indicating zinc and sulfate recombine, recrystallization. So therefore, we keep 50% methanol and water as a component as a solvent for our electrolyte. This hybrid electrolyte actually can improve the wettability. We can see contact angle decrease. That means the methanol preferably absorbed on the surface, prevent the side reaction between zinc and water, and superize the hydrogen evolution. So zinc copper asymmetric cell in this hybrid electrolyte exhibit very good plating strapping reversibility with the average cooling efficiency 99.7%. And the very amazing thing is this hybrid electrolyte improves the low temperature and high temperature performance as well. You can see for the bare electrolyte at -20 degrees that frozen, but for the hybrid electrolyte, even at -40 degrees, still keep liquid state. And you can see at -10 degrees, the cell zinc copper's asymmetric cell has cooling efficiency 99.5%, which is very promising. At 60 degrees, the reversibility also better than the baseline electrolyte. So last work I want to share with you is regarding the how we can enhance strength the oxygen hydrogen bond to stabilize the water and reduce the side reaction, therefore achieve better reversibility of the zinc anode. So in this case, to keep the electrolyte non-flammable, we use fire retardant TMP as one of the components. And in order to enhance the oxygen hydrogen bond, we're adding a high polar solvent, which is DMAC. So this DMAC is an electron-rich component. So it helps to increase the electron density of the protein in the water. So you can see from the FTIR spectral, the peak has an obvious blue shift, indicating the hydrogen bonding between water reduced, but the hydrogen bond in strength. Also from the NMR, we can see there's a shift of this water, the peak relevant to water shifted to a lower chemical shift ppm, 3.52 around. So indicating the electron density increase. So the oxygen hydrogen bond becomes stronger. So due to the stronger oxygen hydrogen bond, the water becomes more stable. So you can see it becomes stable even charged to 2.25 volts. and the zinc copper asymmetric cell can achieve much better cooling efficiency, 99.5%. Also, we found that the zinc deposition behavior changed in this electrolyte compared to the normal aqua-based electrolyte. The surface energy along 002 plane is the lowest, indicating it is the orientated, preferred orientation. So therefore, the zinc deposition has 002 plane orientated deposition. In this way, we can achieve dendrite-free zinc anode in this hybrid electrolyte. So the zinc symmetric cell has very good, reversibility. Then we coupled the zinc with zinc vanadium pentoxide to construct a full cell and test the full cell battery performance. So here I would like to mention the mass loading for the cathode is quite high, 6.6 milligram per centimeter square. The cell can be charge-discharged for 3,000 cycles. Capacity retention about 80%. And we from the in situ synchrotron powder diffraction analysis, we found that the you can see in the baseline electrolyte the peak shift to a lower angle significantly, but in the hybrid electrolyte, the peak shift is much smaller, indicating the strain the structure change is smaller. So possibly due to the in the hybrid electrolyte, less water solvated with zinc ion. So therefore, the structure change is smaller during charge discharge. Structure stability better for the cathode material. And this hybrid electrolyte can be the zinc battery, zinc vanadium pentoxide, full cell can be charge discharged at high temperature, 70 degrees for 1,400 cycles. And it also can be charge discharged at minus 40 degrees. You can see nearly 2,000 cycles. The capacity is still quite stable. There's no obvious capacity fading. So basically, this by using this cell or this electrolyte, zinc battery can be charge discharged at very wide temperature range. So all of this work was done by my PhD student and postdoc fellows. I would like to take this opportunity to thank them for their hard work and also the financial support from Australia Research Council. Thank you for your attention.